We'll now move to our last talk for this session from Evan Schneider. Okay, great. We have the slides. All right, it looks good. So Evan will be speaking. Evan is from University of Pittsburgh, and she will be speaking more about outflows and multi-phase outflows. So take it away.
Thanks, Christine, and thanks to all the organizers for putting this together. It's been really nice to just take a break from the real world and get excited about science again. I know, given the current circumstances, it's been a little bit hard for me lately. So it's been really nice to just have something get me excited again. So I'm gonna talk about multiphase gas and mixing and acceleration and outflows, and actually Pratik's question or comment set me up really well, because I am gonna try to focus a lot on resolution in this talk, and what things I think we are sort of converged on, and where we maybe need a little bit more work. And so this is of course stuff that I've been doing with many great collaborators, at least a couple of whom I think are here. And so I also have to echo what Max said yesterday. I was kind of under the impression this was going to be a little bit more of an informal conference, and so this may resemble more of a grab bag of thoughts than a coherent talk. And also I basically provide no introduction. So this is your introduction with apologies to folks who have not been thinking about this a lot. But the idea is, right, in galaxy evolution, we care about multiphase gas, and I'm particularly interested in this question of, multiphase gas and outflows, which, yesterday we saw some talks pointing out that this is a common phenomenon, and how much do we need to understand about the multiphase character of outflows to inform our sort of larger theories of galaxy formation, and effectively, this is a great drawing from the 2017 review, and so what maybe is still missing from this picture. And so the laboratory that I'm going to be discussing today, which is familiar to some of you, but not all, so I'll briefly describe it, is this series of simulations I've been carrying out over the past few years, which I call CGOLS. And the basic idea is these are just global simulations of outflows. The schematic on the left shows you what our simulation setup looks like. The idea is that we are going to take a disk, an isothermal disk at 10 to the 4 Kelvin of gas, and we're going to drive an outflow from that disk. So we don't do self-consistent star formation and feedback. We're just going to inject mass and momentum in various ways in order to drive gas out. The key feature of these simulations that makes them unique is the resolution over the scale, right? So these are going to be run in a box that's 10 kiloparsecs on a side, 20 kiloparsecs long. And we, in our highest resolution runs, we achieve a constant resolution across the entire simulation grid of 5 parsecs.
That was perfect for you.
There, thanks for muting Mordecai there. Okay, so the idea then is that we have several different resolutions, so we do have the ability to check for convergence in various things that we want to measure. And as I said, we're going to apply the feedback in these simulations in a sort of ad hoc way, but I'll argue that it's a sort of resolved way. And what I mean by that is we're going to inject, for the simulations I'm showing today, mass and energy into clusters at various places throughout this disk. And the rate at which we inject mass and energy in these clusters is set by smaller simulations that we run where we actually resolve a multi-phase ISM. Right, so these are commonly called sort of super bubble simulations. The idea is we take a thermal instability or turbulence generated ISM box. We start injecting mass and energy in the center at a rate consistent with whatever our cluster mass is. And then I can measure the flux in mass and energy through a sphere at some radius. In this case, it's radius of 30 parsecs. And that sets the rate for mass and energy injection in the clusters in my global simulation. And so what I mean when I say resolved is that the clusters in my global simulation are all resolved with at least a few cells. And I'll touch on that point later. So this is what one of these simulations looks like. This is a 3D temperature projection through the volume. And what you'll see is, I start turning on these clusters. In this case, the clusters are located in a central region in the disk. So they're spread throughout the central kiloparsec. And they all represent fairly extreme sites of star formation. So each cluster is representative of, a 10 to the 7 solar mass cluster. There are reasons for that. I can get into it later if people are interested. But the point is, if you look at this outflow, then the purple color shows you the 10 to the 4K phase, and the orange and yellow colors are showing the hotter phases, primarily 10 to the 6 to 10 to the 7K gas. And as this simulation evolves, we evolved it for about 75 million years, you can see the properties of the outflow are few of them are consistent. We always see these clouds of dense, cool gas in the outflow, surrounded by the volume filling hot phase. We see variations in the outflow as a function of time, and that primarily has to do with our cluster feedback, how many clusters are on at any given time. So I'll now show you the same simulation, but these are slices. So on the left is density, the center is temperature, and the right is a velocity, a radial velocity slice. This is through the midplane, so you'll see because these clusters are rotating in the disk, they'll sort of come in and out of view. But this just highlights again that the central feature is that we always are generating a multi-phase outflow, and that you can see there are obvious correlations between the density, the temperature, and the velocity in these simulations. This is one of our highest resolution simulations. The resolution is 5 parsecs, and as I think Cameron mentioned yesterday, in cosmological simulations, we always see structure down to the grid scale. So I would not say that in these simulations we are resolving the smallest scale clouds, but as I'll get to in the next few slides, it's not clear that that's the scale that's important if we're looking at seeing more macro features of the outflow. I'm now going to show the same slices, but on the right is a passive scalar variable. So I'm calling this color, right? This is like a dye that you inject into the gas. The point of the color is so that we can track gas that was initially in the ISM versus gas that we inject as hot gas in the clusters. So hot gas in the clusters has a color of 1 or yellow. Cool ISM gas has a cluster of 0 or blue. Key features that I want you to notice here are that there's a lot of mixing going on, right? If you look in the outflow, most of the gas is purple, right? It's a mixed color. But also, there are often correlations between color and density and temperature. But for example, if you look right now, there are not always correlations between color, density, and temperature. So it is true that I think regions that have cold dense clouds seed more cold dense clouds. This is consistent with the picture of cloud growth in outflows that Max and Christoph and others have been talking about. But it's not necessarily the case that you need to seed all of your cold gas in an outflow this way. So the first takeaway I just want to mention is using this color variable, this passive scalar. I think we've been able to demonstrate pretty definitively in these simulations that the momentum in the cool gas is transferred via mixing with the hot phase, right? And the reason I say that is that if you go through the algebra, you can come up with a linear relationship between the velocity that the cool phase gas should have and its color. So here in this equation, I'm representing color with this variable s. And it should be a linear relationship. And in fact, you can predict the slope of that linear relationship. This is a histogram between color and velocity, color coded by mass. And the slope should go as the velocity of the hot gas divided by the color of the hot gas. And that's the line that's plotted here. And what you can see is that, the locus of cool gas in our simulation, this is all measured in just the outflow, follows this linear relationship pretty well. So that's the first takeaway, is that our simulations demonstrate that the momentum in the cool phase is entirely consistent with having been transferred exclusively via mixing, right? You don't need ram pressure, for example. So now I want to talk a little bit in a little bit more detail about these, these sort of macro properties we might be interested in measuring in these simulations. Don't pay too much attention to the specific values on the y-axis. This is measured in a cone, so it's not representative of the full outflow. But the thing that I want you to take away here is this is a plot of the mass outflow rate as a function of radius. I've split it into different temperature bins. So red is the hottest gas, blue is the coolest gas, and green is intermediate temperature. And so the the key features here. One, if we exclude the inner 2 kiloparsecs, which I'm going to do for the sake of this talk, just because that's a region where we're still sort of collecting mass in our cone. You can see that the net outflow rate is fairly flat. So I'm going to use that to argue that this is a roughly time steady approximation for our outflow model. Another is if you look, at 2 kiloparsecs at the red and the blue lines, we see very similar mass outflow rates between the cool gas and the hot gas. And I'm not going to talk a lot more about that right now, but I think it's interesting because I think it's actually pretty different than what is seen perhaps in some of these ISM outflow simulations. And maybe that's something that's worth discussing later. The momentum outflow rate, right? So since the mass outflow rate is roughly comparable between the phases, that means the hot gas is moving faster, so it's got more momentum. And of course, the energy outflow rate is completely dominated by the hot gas. We don't see a ton of energy loss in these outflows, partly because we did use this sort of extreme cluster model. So there's just not a lot of time for the energy loading to be decreased via interaction with the ISM gas. And so that's that's another caveat to what I'm saying. Okay, so mass, momentum, and outflow energy rates. What do I want to say about this? Well, they're basically converged. So this is the same same plot of mass outflow rate, but now I'm showing, in addition to the different temperature bins, the resolution of the different simulations shown with these different lines. And there's a lot of squiggles here. We could get into arguments about well, it looks like maybe the highest resolution there is a little bit more transfer or more gas in the cool phase, right? But the point is that these are all well within of order unity each other, right? And there's no clear trend, I would say, with resolution here, other than maybe from higher to lower, you have slightly more mass in the cool phase versus the hot phase. And that's true also for the momentum and the energy. And in fact, the momentum and energy, if you divide out the mass, the differences in the mass outflow rate, you find very consistent results. So that's good, right? Because that means, I think this is sort of consistent with what Drummond was saying yesterday. If we're resolving the sort of large scale turbulent structure, the eddies that are responsible for transferring mass from one phase to another, then maybe we're okay on these large scale properties that we care about. And I think this is also good from the perspective of doing global galaxy simulations or even cosmological simulations and zooms, right? I think this sort of indicates that perhaps if we can resolve some form of reasonable feedback in the ISM, maybe we can actually trust the outflow predictions a little bit better than we thought we could. Because it was mentioned yesterday, I thought I should touch on this question of cool cloud growth in the outflows. Right, so if you were thinking back on the slices that I showed, it's clear there are plenty of clouds in this simulation that pass the radius criterion, both the one that Max pointed out and the one that Pratik was talking about from the Lee paper. So why is it then, if I look at the mass flux or the mass outflow rate of cool gas as a function of radius, it's clearly falling off with radius, right? Which would indicate the cool clouds aren't growing. And I think Max, kind of pointed this out because I have yelled at him many times. I'm impressed that now I was in class when he was speaking, so I couldn't actually be yelling in the background, but he did it for me, right? The answer is that these are not laminar flows, right? If I plot the velocity difference between the velocity and the expected radial velocity in the outflow, it's extremely turbulent, right? It doesn't look like this long box where particles can recondense, and so I attribute the fact that we don't see mass growth in the outflow to this turbulence, and in fact it's almost worse than that, in the sense that it's actually the cool clouds in the outflow that are responsible for generating the turbulence, to a certain extent. And so, you know, in Max's sort of Day of the Dead, I was watching his talk late at night and writing this. Sort of like, okay, so they're kind of foretelling their own doom, right? Because the clouds are there, they're generating turbulence, and that makes it so that they can't survive for a longer time. So, so I think that's another interesting point, right? Is just that just because you have cool gas entrained at large radii and winds doesn't necessarily imply that you are growing that cool gas mass.
5 minutes.
Briefly, I want to 4 minutes.
5 minutes.
5 minutes. Okay. So I wanted to briefly touch on the gas profiles. I'm not going to say very much about this. I think Todd might talk a little bit about it in his talk. But if we look at the profiles in the hot gas as a function of radius, here you can just focus on density in the upper left. I've plotted in these plots you know, in solid lines, the expectation for just a sort of Chevalier and Clegg type outflow. And the point is that, you know, in the density and the pressure and the temperature, we find slopes that are well above what are much flatter than what you would expect in the sort of just generic adiabatic outflow case. And that I think we can attribute to the mass transfer. So you have to account for a mass source term in your equations in order to reproduce the hot gas profiles. And so that's, you know, that's kind of takeaway number 3 here, is just in order to get these profiles right, you need to account for the presence of both phases. Okay, I'm not going to say too much more about profiles other than, you know, we can look for convergence there too. It looks pretty good with the exception of perhaps velocity. So this is for the hot gas. What we see is that, you know, the smaller the resolution, the more it looks like the velocity in the hot gas is decreasing. And you see the exact opposite in the cool gas, right? So if I look at in the upper right here, the cool gas velocity as a function of radius, you see that it does slightly increase as we increase the resolution. And I think this makes sense in the context of this mixing model, right? It's effectively how much time do you have to mix as a function of your travel through the box. And the shorter the resolution and the smaller the resolution, you know, the more efficient the mixing, and so the more efficient the momentum transfer from one phase to the next. So that's an interesting area, right? In order to get the velocities right, we might need higher resolution. But on the whole, you know, I would say that these profiles and the outflow rates are more or less converged. So that's another win, I think. What about the phase distribution? So here's the phase distribution for 20 parsecs. Here's the phase distribution for 10 parsecs. Here's the phase distribution for 5 parsecs. It gets less noisy, but I would say on average looks very similar. Again, we find similar amounts of cool and hot gas between these 3 simulations. So at this point, you're probably saying, okay, Evan, then why did you waste all these, you know, millions of core hours running these high resolution simulations if you're telling me everything's basically converged? And for me, the answer is that the intermediate phase gas is really where we're going to distinguish between these different models. So if I plot now, and this is a super simple way of creating fluxes, so forgive me if you've done this in more detail, but I'm just going to assume that ions are you know, collisionally ionized and plot things according to the temperature where the maximum of the collisional ionization is. Okay, so that's what I mean by silicon 2 just means 10 to the 4 K gas, right? Oxygen 6 means 10 to the 5.5. But if I do that, and then I create something that looks like a, you know, down the barrel type observation of fluxes, if I do this for 20 parsec resolution, I see this. If I do this for 10 parsec, I see this. If I do it for 5 parsec, I see this, right? So increasingly, we're populating the intermediate state ions, particularly at the high velocities. So this, I think, is nice because it means, you know, perhaps the takeaway here is that we do need the higher resolution to populate these intermediate state ions. And so maybe this means that contrary to the, you know, the overall mass or energy fluxes between the phases, the ion population goes more as the mixing area in sort of Drummond's terminology, rather than the total cooling volume. I think I have like 1 minute left, so I will just briefly throw in there that, you know, the model also has a role to play. If I run the same simulation, but I distribute the clusters throughout the disk, right? It looks something like this. I've been told that the simulation, the view on the right looks something like a petri dish. And the point is, we still get a multi-phase outflow. We see cool gas clouds. Because this has a distribution of cluster masses, the profiles aren't exactly the same, but they're qualitatively similar. The phase diagrams between the centrally clustered and the distributed cluster formation look relatively similar. But again, the intermediate state ions between these two models look really different. So the left is the model I was talking about most of this talk. The right is the distributed star formation. We see there's a real discrepancy between these. And I actually think this may be a win too, right? Because even though it means it might be harder to untangle the effects of resolution in this case, it might be telling us something physical about what's happening in the outflow. So I've also just included on the bottom of this slide for fun a couple of silicon-4 profiles from John Chisholm's 2016 paper. You can see there's structure in those profiles that's sort of reflective of the different structures we see in these, quote, down the barrel observations. So perhaps even more than the resolution effects, the model dependence of these intermediate state ions is something that will allow us to distinguish models. And I'm sure this could also be applied, right, in the case of many of the other pieces of physics that we've discussed so far in this conference. Cosmic rays, for example, I would expect to give a really different looking profile. So I'll finish with that. This is just a restatement of the takeaways for this talk. I'm sure that's there's 5 takeaways. That's probably 4 too many for a 20-minute talk. But I'll leave it there, and we can move on to questions. Thanks.
Okay, thank you. Excellent talk. So I think we'll go to Kartik first.
Yeah, just wanted to ask you this question about the gas density, effect of gas density on the formation and destruction of these clouds. Basically, I assume that your simulations are with high star formation rate and low circumgalactic medium density, right?
Sure. We vary the quote star formation rate from 20 solar masses a year to 5 solar masses a year. But yeah, I guess that could be counted as high.
So for lower star formation rate and let's say a high CGM gas density, you will have the internal shock, which is much closer than what you see in your simulation, right? In your simulation, it goes away out
Definitely.
of the box. So what happens when these cold clumps cross this internal shock? Are they still alive? Are they getting destroyed? So do you have any idea what happens there?
Yeah, I think this is a great point. And I want to actually sort of expand on it and say, right, these are very idealized simulations where the star formation, a hot outflow is always there to power what's going on. But in fact, I think that in addition to, additional CGM mass relative to the pressure in the hot gas phase, or additional time variability in the star formation rate, I think these things all contribute to potentially cold gas formation. And part of the reason I say that is there's a point in the simulation where I change the properties of the outflow by lowering the star formation rate, and I see a buildup of cold gas at that point. So I think that's, you're right to point out that both the surroundings and the actual physical picture in which these cold clouds are formed is going to affect whether or not they survive. And I think that's something we should all be taking into account as we're performing these idealized simulations, is what is the bigger picture. And in the observational systems that we compare to, we definitely have to take that into account, right? M82 has this big sort of cap in H alpha, and I think that could very easily be related to say burstiness of the outflow process.
Yeah, I was thinking in the line that if you don't have clouds, or clouds get destroyed in the internal shock and don't travel further away, we can maybe put some constraint on the CGM that the outflow is moving through from this observations. If you see, you find some such physics that is destroying the cold clouds.
Yeah, no, I think you're right. Right, if the properties of the outflow are consistent with there shouldn't be cold clouds at 15 kiloparsecs, and you see cold gas at 15 kiloparsecs, I agree with you. That indicates that the formation may be related to, say, material in the CGM and the outflow interacting with it.
So maybe we can continue that discussion later so we can get some more questions in. So we'll go to Cameron and then Frank. So Cameron.
Yeah. Hi, Evan. As always, excellent talk. Really insightful points. Thank you. I had a question about the resolutions. So the fact that you were talking about you didn't see any major differences in the momentum, mass, and energy transfer between your three different resolutions, between 5 and 20 parsecs. Have you done any like super chromo, well, for you, super chromo resolutions like 50 or 100 parsecs and seeing if you see deviations in that? Because like the best we're able to do with the cosmological is, you know, a few hundred kpcs, or I'm sorry, a few hundred parsecs. So somewhere in between your 20 parsec and our few hundred, it'd be really nice to see like where the break in functionality and where that convergence actually occurs.
Yeah, I think it's a great point. I mean, I think it comes back to, right, what's the scale of the sort of largest eddies that you care about,
right,
in this mass transfer process. And you know, I haven't done lower resolution simulations because at the bare minimum, I need to resolve the clusters in the ISM.
right.
And I'm giving them radii of, you know, 30 to 50 parsecs. But I think that, you know, it's relevant, particularly in the case of, right, zooms and things like that, where you degrade the resolution outside of the ISM. You know, right, what scale of sort of turbulent eddies do we have to capture in the outflow in order to still capture the, you know, the mass transfer and momentum transfer and energy transfer between phases? I've not done that experiment at lower resolution, but I think you're right that it would be useful to know.
And do you think, just as a minor add-on to that, do you think capturing those three different fluxes is sufficient to say that we're resolving the structure and all the behavior? I mean, obviously at a hydrodynamic standpoint, that seems to be the case, but then you were talking about the intermediate ions might be different, and the behavior of thermal instability might be different, these sorts of things.
Yeah.
I don't know. I just wonder, it seems like there's a lot of different resolution effects on a lot of different pieces of physics, and what works for one aspect might not work for all. And so I don't know. It's a hard.
Absolutely, yeah. And I'll just give a short answer, which is that's kind of what I wanted to bring up with this talk, is it totally depends on what your goal is. Is your goal cosmological galaxy formation? Then like maybe you're doing okay. Maybe this is why cosmological simulations can get reasonable mass functions. Is your goal to compare to down the barrel observations in order to determine mass outflow rates from galaxies? Then you're going to need much higher resolution, right? And I think this is relevant in our comparisons to the CGM, particularly, where we're trying to compare cosmological simulations to observations. That's where I think it's worth pointing out that it can make a big difference to the observables.
Okay.
Cool, thanks.
Continue that discussion later again. Frank?
Hi, Evan. Just a quick question for clarification. Looking at your movie, it seemed like, you know, you had a lot of very cold gas spewing out of the center of the disk, and I was just wondering, could you clarify the sourcing of your outflow? So you said you dump energy and mass. Are you actually just accelerating cold gas directly, or that's resolved? I'm trying to see how you're supposed to accelerate the cold gas out of the disk.
Yeah. So right. So it's both, right? And that was kind of the point of this color. If we watch the movie again, just so you can, right, like look at it as I'm talking about it, right? If gas in outflow is dark blue, it's ISM gas that has been directly accelerated by one of the nearby clusters, right? But if it's not blue, it's been mixed. And so the acceleration by and large is a result of momentum transfer via mixing. But yeah, the source of the outflow is ISM gas that's getting lifted up by being next to one of these clusters.
So the yellow is dense, cold, or hot?
Sorry, yellow is hot. Yellow is hot cluster injected material. Blue is cool ISM gas.
Okay.
And if we looked, I mean, we can't do this in this context, but if we look at very high resolution near the center, you will see there are tiny blue blobs, like essentially pure ISM gas, very near the midplane, but they get shredded and mixed. And so as you know, as time goes on, this mixing becomes the more important process.
Okay, gotcha. Thanks.
Mhm.
Okay, so maybe we'll have one last question from Mordecai, and then we will move to the coffee break.
So I was pretty much going to ask a variant on the same question, which is the cold gas in the outflow stuff that was heated up to intermediate temperature during the mixing process and then cooled again, or did it actually stay cold during the acceleration and expulsion process?
Yeah. Okay. So, I don't have, this is not a particle-based code, so I can't take a single parcel of gas and tell you what temperature it was at all times. But I can say a couple of things. One is this plot has me completely convinced any gas that's been accelerated, cool gas, 10 to the 4K gas that's been accelerated, has been mixed, right? In order to know how hot it got, though, I need to know, how much mixing and in what stage, right? If I take a relatively large amount of 10 to the 4K gas and mix it with a relatively small amount of 10 to the 6K gas, I get intermediate temperature gas that's not very hot.
Mm-hmm.
If I do the opposite, right, I get intermediate temperature gas that's quite hot. And so I think where you fall on that threshold actually determines whether or not you get to cool back down and continue as cool phase gas on your way out. But yeah, I mean, so effectively, right, I think any cool gas that's been accelerated has been mixed to warmer temperature at some point, but how much warmer is difficult for me to say.
Thanks.
Okay, so I think we'll wrap it up here. Thank you to all of the session speakers. We had 3 excellent talks.